We will now talk about a notion of graph isomorphism. And this notion is basically about when you look at two graphs, are these two graphs the same or not? Or are they equal or not? Again, when we have two numbers, if someone gives you two numbers, one is 7 and one is 7, and you are asked, are they equal? Yes, of course they are equal, they are the same. If you are given something like x minus 2, x plus 2, and another term is x squared minus 4, someone asks, are they the same? Or are they equal? Of course, they don't look the same, but yes, they are equal. These are the same, right? So we can talk about them. Now the question, if I give you this graph, A, B, C, and I give another graph, 1, 2, 3, are these two graphs the same? Okay, so what does it mean? Of course, they are not the same graph because they are two different objects that I drew on the slide. And one is labeled by ABC, the nodes are labeled by 1, 2, 3. Now, it turns out that yes, we can treat these as the same or are as equal. If we forget about these labels 1, 2, 3 and ABC, we can actually map one graph to the other to show that they are equal graphs or they are the same graph. And this is what graph isomorphism is about. Okay, so formally, if I'm given two graphs, G1 and G2, and we say graph 1 is isomorphic to graph G2 if we have a bijection from V1 to V2, we have a bijection from the set of nodes of the first graph to the set of nodes of the second graph. This bijection, it immediately tells us important things. One is that V1 and V2 are of the same cardinality or the same size, right? So the two graphs, if they are isomorphic, they have to have the same number of nodes. Then we have this condition here that tells us that if there is an edge between two nodes UV in one graph, then there is an edge between their images in graph G2. Okay, so if UV and G1 have an edge between them, their images in G2 have an edge between them. Okay, so let's look at examples of graph isomorphism. So if I look at, again, if I look at something like this here, this is the simple example, A, B, C, and 1, 2, 3. These are the two graphs, G1 and G2. And I say, are they isomorphic? Yes, I can actually take the bijection function from the nodes of G1 to the nodes of G2 as define it as follows. I can map A to 1, I can map B to 2, and I can map C to 3. And if you check here, there is an edge AB in the first graph. Is there an edge between f of A and f of B? Yes, there is an edge between f of A is 1, f of B is 2, and there is an edge in E2 between 1 and 2, right? So there is an edge between B and C in the first one. Is there an edge between f of B and f of C in the second graph? F of B is 2, f of C is 3. Yes, there is an edge between 2 and 3 in graph 2. So these two graphs are isomorphic, okay? Now, if you look at these, you say, okay, these are very simple, but one can actually draw graphs that it's not obvious whether they are the same or not. So let's look at graph like the complete bipartite graph on 3 nodes, on 6 nodes, sorry, 3 on each side. So if this is 1, 2, 3, 4, actually let me label them the odd in one side, 1, 3, 5, 2, 4, 6. And let's look at another one, another graph here. And let's label this, let's say A, B, C, D, E, F. And let's define the edges as follows. So there's an edge between A and B, there's an edge between C and D, D and A. So we have this square here, these 4 edges. then we have these edges, and one between E and F, and then we have D and E, and we have F and A. Okay, so this is the graph. And because if you look at them, they don't look the same at all. But are they the same? Are they the same graph? Are they the same graph here? The answer, or are they isomorphic? The answer is yes. And one function, or the function that we can come up with, is that if I look at node U in V1 and I look at f of U in V2 here, so in node 1, 2, 3, 4, 5, 6, what do I map them to? So I have, for example, node 1, I can map it to node, let's say, F. Node 2, I can map it to node 2 here, I can map it to node E, let's say, and I will verify it at the end here. Node 3, I can map it to node D, and node 4, I can map it to node C, and node 5, I can map it to node B, and this leaves 6 goes to A, right? So 6 here will go to A. Yeah. So if we look at this function here, so I basically give a bijection here, right? Because it's one-to-one and onto function from the nodes of G1 to the nodes of G2. Now we need to verify, is it true that an edge exists between U and V in G1 if and only if there's an edge between f of U and f of V in G2. I'm not going to verify each one of them here, but let's look at some of them, at like a couple of them. So there is an edge between 1 and 2 here. Is there an edge between f of 1 and f of 2? F of 1 and f of 2 is f and e. Is there an edge between f and e? Yes, there is an edge. Okay, let's look at the edge between 2 and 5, this one here, 2 and 5. F of 2 is E, F of 5 is B. Is there an edge between E and B? E and B, yes there is, and it's this one, and so on, right? So we verify them, but also you have to verify that if there is no edge in G1, of course there has to be no edge in G2. So there is no edge between 1 and 3 in G1, and there is no edge between F and D in the second one either, right? So you can verify that there is an edge between U and V in G1 if and only if there is an edge between f of U and f of V in G2. So this is an example of isomorphic graphs. We can, it's very easy to come up with graphs that are not isomorphic. Here is an example. So this is a graph on 3 nodes, 1, 2, 3. And this is a graph on 3 nodes, A, B, C. These two are not isomorphic. No matter what function, what bijection you come up between the set 1, 2, 3 and the set A, B, C, you will find the case that there is an edge in G1 and there's no edge between the images of its nodes in the graph G2. Okay? So when we talk about isomorphism, think about them as in the sense that can you redraw one of the figures, one of the graphs, so that it looks exactly the same as the other graph. This is really what it means for isomorphism. Can you rearrange it on the paper so that it looks exactly the same? Okay, and this is the formal definition, is that if we find a bijection from V1 to V2 such that there is an edge between UV in G1, if and only if there is an edge between f of U, f of V in G2, then the two graphs are isomorphic. Sorry. The second and last concept in this here is the subgraph isomorphism. So graph isomorphism is telling us the two graphs are the same. Subgraph isomorphism tells us that one graph is really a subgraph of the other here. Okay, so we say graph G1 is subgraph isomorphic to graph G2 if G1 is isomorphic to subgraph of G2. Okay, so for example here, let's take G2. Let me draw first G2, So suppose we have this graph A, B, C, D, E. If I take the graph one, two, three, four, this graph G1, if this is G2, G1 is subgraph isomorphic to G2, okay? But if I take the graph, let's say here, K, L, M, N, if I take this graph, and this is G3, G3, can you find a subgraph of G2 which consists of 4 nodes such that they are connected like this in a square? The answer is no. So G3 is not subgraph isomorphic to G2. Okay? So this is the concept of graph isomorphism and subgraph isomorphism. I will finish here with 2 points about graph isomorphism and subgraph isomorphism. Okay? So let's again, so suppose I have the set A is the set of all graphs, on n nodes, let's say. Okay, so all the set of all graphs on a node and on n nodes, and I define the relation G1, G2. I define a relation on this set A, binary relation on set A. G1 is isomorphic to G2. Okay, so I put 2 graphs. I say that graph G1 is related to graph G2 if G1 is isomorphic to G2. If you look at this relation, every graph is isomorphic to itself. Right? So in other words, G1 and G1 is in this relation for every G1 in A. Also, if G1 and G2 is in the relation, then it's also G2, G1 is in the relation. The reason for that is because with the function we have is a bijection. So if we have a function that's a bijection, so if is the bijection from G1 to G2, then what is the bijection? What is a bijection from G2 to G1? It's the inverse of that function. So we have a bijection from G2 to G1. In other words, if G1, G2 is in the relation, then G2, G1 is in the relation. The third point here is that if G1, G2 is in the relation, and G2, G3 is in the relation. So what is this saying here? These are the sets of nodes. I have bijection F from V1 to V2. I have bijection G from V2 to V3. Do I have a bijection from V1 to V3? The answer is yes, and it is the composition. Actually, I can compose G on F. You apply F first, it takes you from V1 to V2. You apply G from V1 to from V2 to V3. You get a bijection all the way from V1 to V3. So what did I show? That this relation R is reflexive, is symmetric, and is transitive, which means this relation is an equivalence relation. Okay? So graph isomorphism defines an equivalence relation on set of graphs. If I look at relation S as G1, G2, and G1 is not isomorphic but is subgraph isomorphic to G2. So we ask, is this relation reflexive? So is every graph subgraph isomorphic to itself? The answer is yes, because it's the same graph, right? So it is reflexive. Is it symmetric? The answer is no, because if a graph G1 is subgraph isomorphic to G2, it doesn't mean that G2 is subgraph isomorphic to G2. In fact, G2 could have even more nodes than G1. It's impossible then to be subgraph isomorphic to G1. It is not symmetric. What about anti-symmetry? If we say graph G1 is subgraph isomorphic to G2, and G2 is subgraph isomorphic to G1, does that mean that G1 and G2 are the same or are isomorphic? The answer is yes, they would be isomorphic. Okay, so equality here, we say G1 and G2 are equal in the sense that they are isomorphic to each other. What about transitivity? If G1 is subgraph isomorphic to G2, G2 is subgraph to isomorphic to G3, is G1 subgraph isomorphic to G3? The answer is yes. Again, you can use composition of the functions that we define on from G1 to G2 and from G2 to G3, and you will get transitivity. So subgraph isomorphism is reflexive, defines a reflexive relation, anti-symmetric relation, and transitive relation on the set of all graphs of a certain number of nodes. So what does that tell us about S? So if we define S on the set of all graphs, then we have S defines a partial order. Okay? Partial order. So graph isomorphism defines an equivalence relation on a set of all graphs, and the relation of subgraph isomorphism defines a partial order as well. Okay, so here notice when I started with A, I defined it as a set of all graphs on n nodes, but you can look at it the set of all graphs on 1 nodes, 2 nodes, 3 nodes, or whatever number of nodes. Okay, so you can basically partition the set of all graphs using this graph isomorphism, because it defines an equivalence relation, and this equivalence relation defines equivalence classes. Also, subgraph isomorphism allows us to partially order the set of all graphs. Which graph comes before the other? Okay. Think about subgraph isomorphism as being similar to subset or equal relation, and think about graph isomorphism as equality between two sets.